So you guys know that it stands for positron emission tomography. It uses it's the use of biological molecules that allow for measurements of metabolic function through SUV values. So basically, what they're just basically trying to say is that the purpose of PET is to evaluate all of these metabolic studies. So cancer, obviously, highly metabolic, and so that's why we use PET as opposed to doing some other study like a bone scan, to evaluate all these things. With these, you can actually get an SUV value, which allows it to see, where what I don't want to say what grade it is, but where it's at as far as the uptake for the FDG. Okay. Other major functions for tomographic imaging. Right, so the SUV value, which is the standard uptake value, estimates the amount of the injected radionuclide that is taken up by the tumor or the organ. It aids in differentiating between a malignant and a benign mass. Okay, so the SUV calculation would be the concentration of activity in the tumor times the mass of the patient times the injected amount of radioactivity that you've given to the patient. And if it's greater than 3, that means that it's a high probability of a malignant tumor. You guys let me know what needs to be written in. I'm assuming it's the red part that needs to be written in, correct? Okay. All right, so the top radio forms that we use. Okay. You guys have to say, that's why I don't know. I can't see you to know if you guys are still writing or need more time, okay? Okay, I'm ready. All right, so the top radio forms that we use would be FDG 18, which is fluorine, the carbon 11, the nitrogen 13, the oxygen 15, and germanium 68. And those are all cyclotron produced. And then you have rubidium 82, your copper 62, your gallium 68, and those are generator produced. Okay? And the most commonly used is going to be the FDG 18. So now, you guys, for the test, you need to know these. Okay? Make sure you know them. There's a difference between PET and for tomographic imaging, but the PET uses only positron-emitting radionuclides. The PET camera does not require the use of collimators. The PET images have a greater sensitivity and greater resolution, but the disadvantage is that it has a short half-life for the radiopharmaceutical and it's very expensive. Why does a PET require collimators? Does not require collimators? Yeah. Because it's usually associated with it's a different type of crystal that's being used also. There's a dedicated sodium iodide PET, but the images are really well done, and the detectors on the PET is different from the regular biocamera. Because I was slow because energy is so high. Okay. But it's a different type of, so it does have something, but it's not like the collimators, because it's still, remember that the PET falls at 180 degrees, so what's happening is that it still needs to hit those detectors, and it's random when that happens. It's, I don't want to say random, but it has a focalized point where it's going, which is 180 degrees in two different opposite directions. So with the gamma camera, it's only going in one direction, which is upward. I mean, yes, gamma's going all over, but it's being detected upward, if that makes sense. Gotcha. I'm mixing it up with something else. Sure. Okay. Positive. Okay. All right. So, sensitivity of the PET. So collimators reduce a camera sensitivity, okay? And the ACD, which is the annihilation coincidence detection, when a positron undergoes mutual annihilation with a negative electron, the rest masses are converted into a pair of annihilated pair of photons. And the photons emit travel by the KEV simultaneously in the opposite direction. The near simultaneous detection of the two annihilation photons allow the PET to localize their origin between the two detectors without the use of collimators. So there's your answer. So it was basically what I was saying, that the fact that they go in those opposite directions, you have the collimators to be able to detect those photons being emitted or being displaced or emitted or captured, I guess you could say, by those detectors. Okay? Any questions, anyone? Okay. All right, so as you can see here, you have an annihilation that happens, and then what ends up happening is that you have the photons are going to be displaced in opposite directions, 180 degrees, and then the detectors are going to be able to, like, can you see my pointer? No. Sorry. Can you see it now? No. Is this better? Okay. Yeah, okay. Alright, so what happens is that here's where you have your annihilation interaction, okay? And what happens is once they combine, they're going to emit two of those photons going in opposite directions, giving 511 keV, and then they're going to strike the detectors. And then from there, it goes into your whole entire circuitry of positioning and so forth and so on displays. Okay? Alright, so resolution of PET. So you have coincidence detection. Two detectors on opposite sides of an annihilation reaction register the coincidence photons on an imaginary line known as the line of response. You need to know that. The line of response is the functional equivalent of a pixel. Each pair of crystals that coincide, each pair of crystals that coincidence allows is made to one other one. Once the coincidence is determined, the tomographic or the tomography identifies the two crystals that register, and then the count is then added to the memory of the local, which localizes it for a specific hour. So what it's basically saying is that once the annihilation occurs, the two photons split, and then they go into opposite directions of the detector in one 180 direction, and then one goes to one detector, the other one goes to the other detector. That's called the line of response. Okay, so when that happens, it is registered by the detectors. And wherever it hits on those detectors, it's kind of like a memory that is inputted saying that it is on, I don't know if you remember when we were doing spec, and then you have to have those numbers, the 1, 2, 3, 4, and the quadrants, and then that correlates to where it is on the positioning circuitry. Yeah. This is exactly what it's doing, but it's on those detectors on opposite ends, okay? And then once it reaches the detectors, it basically gives a sensitive position on the actual matrix so that it can be displayed. Does that make sense? Yeah. Is Abby the only one that understands this? No. Okay. Just want to make sure. Right? So this is exactly what happens. You have your annihilation, and then you have an electron, and you have a positron, and basically what's released are your two photons, and you have 115 keV that's released, and they're both unreleased at opposite ends, equaling 180 degrees. Okay, same concept, but now with an actual person or an object, and this is what will happen. Okay? right, so now we're going to continue with the resolution of PET. So now there's a thing called time of flight. Assumption that the localization of the imagination can be localized along the line of flight of the coincidence photons by measuring the time of arrival of each photon at the opposite crystal. So one photon usually arrives before the other. The time difference is proportional to the difference in the distance traveled by the two photons and is then used to calculate the positron event along the line connecting the detectors. Due to the electronic time limitations, this method is not accurate and reduces spatial resolution. So what they're trying to say is there anything right here? No. Okay. So what they're trying to say is that, let's say annihilation occurs here. And they're saying that one will ideally get to the detector faster than the other. Okay? That's time of flight. So because this one gets there faster, it's going to register this resolution as opposed to this one. Not that it won't accept the resolution here, but it's not going to be as accurate as this one. So ideally what you want is you want it to be from here and then both trying to get there almost at the same time, if that makes sense what I'm saying. The one that gets to the detector first is the information that's being registered from resolution. Okay, that's fine. So anything following after that, the resolution gets not distorted, but it's not as accurate as the one that hit the detector first. Okay? Yeah, but I mean, there's no way we can control it. That's correct. That is very correct. But that's why you have the software correction. That's why you have a larger patient. Do you want to give them more FEG or do you want to give them less? More, okay. Because you want to make sure that you have enough photons to actually strike the actual detectors, correct? Because you have a lot of body mass that you've got to get from, right? Okay, so if you have all that body mass to get to, what do you think? It's slowing it down. And it works as an attenuator as well. So you have to remember all those things that come into play. Okay? Alright, so now you have different events. So you have coincidence events, also known as a true coincidence event. And then you have single events, and then you have random events. So the coincidence event, you have a single positron annihilation producing a pair of photons that hit the opposite detector simultaneously, which is normal. Okay? True event. Then you have single events, and this can occur in one of three ways. So the first one is that you have a single non-annihilation journal that impacts the detector. Then you have one out of the plane photons that leaves undetected and another photon hits the detector within the plane. And then you have the third one where only one photon impacts the detector and the other is static or absorbed. And then you have your single event, which are being projected. Okay? Then you have your random events, which produces one false positive, and the probability of random events increases with increasing radioactivity. I did it. You guys are not saying anything, so I should be better still ready. Just have the text line is ready. Okay. I must have much more. 1, 2, 3, 4 little lines. Oh, wow. 4 little lines. Good job. Oh, wow. Oh, my God, it's all. That's right. Ready? Yeah. Perfect. So this is what happens, right? You have your coincidence event, which is the true events, where you have your annihilation, and then you have your two photons going in two opposite directions. This is what you want, okay? This is exactly what you want, right? The annihilation occurs and it goes in the opposite direction, 180 degrees. Everyone's happy, okay? Yes, you're going to have a difference in the time frame of when one reaches the detector and versus the other, but that's normal and it's okay. Alright? Then you have your single event, right? So with the single event, you have the annihilation occurs, but then you have this happen. That's the single event that happens. Alright, so you have for a single event, this is the one with the constant scatter. So you have the annihilation, and only one photon hits the detector, and the other one is lost or produces scatter. And never gets to the detector, but it just produces scatter. So that could be either through interaction with the patient or tissue, whatever it is. Okay? Then you have your out of place. So this one is annihilates, and then you have your photons that are being displaced. So one actually hits the detector, but the other one goes actually through. Okay? So it doesn't actually, it comes out. Okay? So it's not read by this detector here because it actually goes out of the plate. Okay? And then in this one here, you have a variation, but only one portion comes, but it's not really registered. So technically, it's not if you have two, if you don't have two, correct. It just gets absorbed. Okay? Any questions, anyone? Alright. So here you have random events, and when random events occur, when you have what? When you increase the frequency. Exactly. Okay, so what's going to happen is that you're just going to have a whole bunch of possibility of scatter. You're going to have possibility of those photons that are being absorbed and not getting to the detector, or not having the other half of it occurring, or you're going to have possible out of plane photons. Okay? So anything that's possible will increase the amount of radioactivity. Alright? Alright, so we're going to talk about that. I'm just going to go into the tech. So you have your crystals. The PET detector consists of one or several rings of crystals, and the rings are sometimes separated by septum. Sometimes. Okay? Ideal characteristics is that you want a short decay time and you want a higher net yield. Right? So with a short decay time, the time required for the radiation, excited molecules of the crystal to return to ground state. During this time, a second photon cannot be detected with long decay time. Fewer numbers of photons detected, then you have, if you have fewer numbers of photons detected, then you have more sensitivity. Basically, you don't want multiple photons striking the same crystal at the same time. Does that make sense? Yeah. You want to be able to give those crystals time to return back to normalization so that it can register each strike that does hit those crystals. you want to avoid environment, basically. And then you have higher net yield. The greater the crystal, net photon output per keV of absorbed gamma energy, the greater the resolution and the better spatial resolution. 20 or more rings are most common. So you want a high efficiency crystal, so you can have better resolution. Tell me when you guys are ready. Okay. All right, so now you have your PET crystals. These are the different types. You have your sodium iodide. It's rarely used because it's low density and the images are poor. And it's hygroscopic. And then you have a VGO, which is most common, and that's non-hygroscopic. Then you have your GSO, your LSO, your LYSO, and the serum added to all three to improve sensibilization efficiency, and all three are non-hygroscopic. So these three are non-hygroscopic, okay? And they have serum that's added to it. Then you have your barium fluoride and, oh my gosh, what's LA? Labrium? Well, can't be labrium, that's a drug. It's something LA bromide, and those are fast sensitization detectors. And those are lanthanum, yeah, okay. And those are non-hygroscopic as well, okay? So the one that you guys probably deal with is this one, and maybe these three. And that really does depend on what equipment you're using. If it's a Siemens, if it's a GE, if it's a Philips, different manufacturers prefer to use different ones, okay? Alright, so a camera with one or more rings. Ideally, you want more than one ring, correct? Okay? Why? Because you can have multiple detection, obviously. So here you have a single ring, a single full ring system, and here you have multiple full ring systems, right? Now, as the patient goes in, more information is being taken because you have all the different rings there, okay? This is what a block would look like. So you have your crystal detector block, right? So here you have, let's say, 1, 2, I can't even say 1, 2, 3, 4 on top, okay? And then you have these going down the side. But obviously, each block here is associated to a PN2. It's the same concept as the gamma camera. The only difference is that it has blocks. Okay? And then those blocks are connected to the PN2. And then it still goes into the same type of circuitry system with a preamp and the amplifier, and then to the positional circuitry with the X, Y, Z, and so forth. Okay? Does that make sense, you guys? Mm-hmm. Any questions so far? Okay. Right, so this is exactly what it does. The photon would come in and strike the detector, right? But the detector, remember, has those blocks within what I just showed you in the last slide, and then it would translate into your PM tubes over here. All right? So scintillation occurs once it comes in, strikes the crystal that's there, and then the light's produced, and then goes into your photomultiplier. Okay? Alright, so now your PM tubes. Many crystals with few PM tubes. Many PM tubes with one crystal. Okay. Many crystals with few PM tubes. Many PM tubes with one crystal. I need to get back to that one. PM tubes. That doesn't make sense. You should have fewer PM tubes and more crystals. Many PM tubes with one crystal. That's not the one crystal. This many PM tubes and one crystal. That should be more gamma because it's one solid flat crystal. Here it's just components that are put together. The slits between crystals, exactly. See, the slits between crystals direct the light from towards the PM tubes. The closer the PM tubes is to the site of impact, the stronger the signal. But you guys understand that anyway. Okay. So do we just overwrite that part that we parenthesis? No, I want to see where I put that in there. I'm looking for my book right now. I mean, I'm not going to look at what's right now, but I'll tell you what. Yeah, because you guys don't even have it on your PowerPoint. You guys just have the split between crystals to text light photons towards the PM tube. Right. So I'm going to look at it and see why it's there. And I'll get back to you guys. Okay. And then we have your septal rings. The septal rings is used to improve the resolution by reducing scatter. Sensitivity is reduced by spatial resolution. Sensitivity is reduced but spatial resolution is increased. So you have a 2D scan of septum, and it belongs to the plane photons, and then you have a 3D scan that does not have septum, and it allows for cross-plane events. Alright, so here you have your detector system, right? So you have your rod source, and then you have the imaging table, of course, your gantry board, and then the detector block, okay? So within the detector block, you would have this right here, okay? You have your septums, your scintillating crystals, and then your PM tube arrays. So it's the same concept as your gamma cannon. Okay, so now you have your block detector. Alright, so with the septum, obviously, you see this detector unit right here with the septum. So the septum would be along the lines of these here, where the spaces would be. And without the septum, it would be just one smooth block into your PM tubes. Okay? Alright, so you have your 2D versus your 3D scans, okay? Where your 2D scan was your 2D scan has the septum, your 3D scan doesn't have the septum. Right, so 2D scan has septum, and the 3D scan does not have septum. Okay? So what's going to happen is that you're going to attenuate a lot of the unnecessary photons that are coming in, and here you're going to have a lot of interaction that crosses over because you have nothing attenuating. It's kind of like the septum is kind of keeping it in track to where it needs to go to get to those detectors versus the one without the septum where they're just crossing over each other. Does that make sense? Okay. Alright, so now you have your pulse height analyzer. It signals from pan tubes are amplified, and they're amplified by the preamp and the amplifier. The pulse height analyzer, must recognize which signals came from the paired 511 KV coincidence photons between a pair of opposing detectors. It's achieved by measuring the size of each signal, which is proportional to the energy of the photon reaching the crystal and recording the time of the detection. The pulse height analyzer determines whether the signal is the correct amplitude to have come from the 511 KV photons interaction with the crystal. Okay, so basically, photons strike the detectors. Once it goes through, and then goes from the preamp tube, it has to go into the preamp and then the amplifier, just exactly like your gamma camera. Okay, but at this point in time, what happens is that the measurement of the size of sensitization that is produced is going to basically aid in detecting where they're going or where it came from, and it's going to tell you the time, like how fast it got there. It's going to tell you the time of detection as well. Okay, so with the parrot, as opposed to the gamma camera, you have a time discriminator, and that records the time the signal was generated. Okay, and then you have your coincidence circuit, which examines the signal's amplitude and determines the time of the signal and where it occurred, within which window. And then you have your coincidence timing window, which usually is set between 5 to 15 nanoseconds. So, photons, you have your annihilation, you have photons, 511 keV, going into opposite directions. They strike a detector, then the detector it goes through into the crystals, and from the crystals, it goes into your photomultipliers, and then from your photomultipliers, it goes into your preamp and your amp. From there, you're going to go into your time discriminator and your coincidence timing window. Okay? Does that make sense so far? It's the same concept. The only difference is that with this one you're now adding time. Okay? I don't know if you guys have fun getting it. Okay. Oh, this is really slow. Alright, so what we have here is you have an annihilation that occurred, and it's going into the detectors in the opposite ends, okay? So you have A that's being registered at X time, then you have B that's being registered at X time, right? So A was recorded sooner than B, if you notice the lines where they're at, right? Okay, and this is the time discriminators. Now what happens is that it moves into your pulse analyzer, And it's going to say, okay, A was registered at this time, and B was registered at this time when it struck the crystals and into the photomultipliers, right? And then from there, the time delay between A and B is, if it's within the limits of the window, then it's accepted. And if it's not, then it's rejected. Does that make sense? And then it moves on into your positioning circuitry. Did that explain it a little bit better? Okay, so like with this one, right? This one would be the example of the Compton scatter, okay? Where you have your annihilation, A actually got to the detector, but B was scattered. Well, I guess I reached it, but it took a long time, right? It's kind of like a long object. Okay, so A obviously is recording the time, B is recording the time here. Right? But now go to your pulse analyzer, and A is going to be accepted because it falls within the coincidence window timing that you set, where it was already set, which is between 5 to 15 nanoseconds. And B is falls well below that, so B is going to be rejected. Okay? Did that help a little bit to explain the whole concept? Okay. It's really the same concept. The only difference is that with this one, you have the pulse height analyzer is being used as a discriminatory for timing, and then with the camera, the pulse height analyzer is for your actual energy. Okay? Right, so then you have nine events that pass. It's true coincidence, which is possible that it does happen. So remember the ones that go all the way through? So if it goes all the way through, sometimes it actually is read as going all the way. So you have A, which went to the detector, and then you have B, who also went to the detector, right? But A's, the other half of A went through, but it got accepted. The time delay between A and B is within the limits of the coincidence windows. The amplitude of both pulses are within the accepted range. So the fact that it actually went through within a specific time frame is the reason why it got accepted.
So, question. Is this two separate annihilation events?
Yes. So you have an A and you have a B, right? So that went through. So the fact that both the second half of A and the second half of B went through, it's only because they went through within that time frame that was set by the coincidence. That coincidence time frame that you guys, or that's set by the machine. Does that make sense?
Got it.
Okay, so it got accepted, and it's considered, and it occurred along the line of response. So those counts were counted. Okay. PET QC. Okay, here we go. All right, so now you have your PET QC, which you guys all, for the most part, have done this, okay? So you have your cross calibration, which is the wall counter calibration, and it's performed quarterly. You guys need to know all of these. The wall counter is a software program that is used to make sure the SUV is accurate, okay? This is pretty important. It's used to calibrate the system response to a known amount of radioactivity and a known volume, and that uses your uranium-68. And then the calibration is necessary for quantitative measurements, such as the SUV, which is redundant to what we just said above. A small amount of the measured radioactivity, which is the positron emitter, is placed in a phantom and evenly mixed. The phantom is then imaged. The accuracy should be within 5% of the activity cone.
Is that an E or a C?
Where are you? Here?
The very last word of
the accuracy should be within 5% of the activity cone.
Oh, it's coincident.
No, it's concentration, sorry. Concentration, activity concentration, sorry.
Okay.
Man, I thought that was an E for cone. All right. Wait, are you guys finished?
Yes.
Okay. So now we have the transmission versus emission. Transmission scan. Position the patient in the scanner and acquire the scan with the activity from the two pre-installed external rod sources or point sources of uranium-68 emitting positron or cesium-137 emitting gamma rays. Then you have your emission scan, which acquires the scan from the patient after you inject them of positron emitters, and the transmission image allows for the correction of attenuation. All right. This allows for a significant improvement in image quality and also a measurement of the amount of radio tracer uptake within the tissues to be performed. You guys can hear that? I'm sorry. Hold on. Let me just tell them I'm in class. All right. You guys have any questions?
Oh, Brian, I'm still.
Okay, no worries.
These are done for every patient?
Yeah. You don't realize it's happening. It's happening as you're acquiring your images. All right, ready? So now here's the difference between your transmission versus your emission scan, right? So you have your rotating source, okay, going like this. Rotating positron emission source, the line of response between a pair of detectors, and these are your ring detectors, okay? It's going like this. And then here is your transmission scan of 511 keV photons. So they're going to the actual detectors, this way or that way and so forth, all right? And then transmission scan with the patient. So the patient's in there and your transmission rod is going around. And then the patient goes in and you're actually acquiring your actual image. So obviously with mathematical algorithms and so forth, you're able to do the actual attenuation correction scans, okay, to make the images look prettier. All right, so then you have your blank scan, also known as your reference scan or air scan, and that's performed daily. Short time acquisition, it's done at the beginning of the day. It verifies that the system is stable and the camera is functioning properly. Scans using the system's internal transmission source or a separate low activity source without the patient in the field of view. Some cameras will perform this automatically by itself at the specific time. So you guys can set it. So I'm sure like there's fancy ones that are set to go ahead and do all these QCs before you even walk in. And then it's going to be displayed as a sinogram. Most common malfunction has to do with the detector block failure. So that means that, like, if you have some kind of issue with that detector, then your PM tubes and everything is basically bad in that one block. One PM tube affects the entire block. Okay? So this is performed daily, and it's a short time acquisition. and it'll be displayed as a sinogram. Okay, which we saw this picture before. You have your pre-installed rod sources that basically go around and do your actual transmission. This is what your normal blank scan should look like. Is that correct, everyone? Those of you that did the PET QC?
Mm-hmm.
Yes? If there was something wrong, where do you think you would see it?
One of those lines.
Along the lines here, right. So what would, if you did see something wrong, it'd be like a big chunk, like that. It's bad. Okay? This is one that's a failed block, so this whole entire chunk is bad. From this starting point here to this part here, so from going across like this whole entire thing is bad.
And that's from 1 p.m. to?
That's from 1. So the fact, because sine waves go like this, like a Z, that's the pattern. So the fact that it's this like this whole entire thing going across up is one chunk because it's a block detector. You remember the picture how it's like one big chunk?
Yeah, I got it.
Right. So this whole part here up is going to be messed up. Has to be replaced.
Just the PM tube or the whole block?
The PM2 because it's not your crystal itself.
Okay.
Okay. All right. So this is the breakdown of the sinogram. So every line. So there's an A, B, C. I don't know if you guys can see it so well, but there's the A, B, C, D, E, F, G, H, I, J, K, L, and so forth, right? Those correspond to, so A and G correspond to each other. Does that make sense? B and F correspond, right? But this also occurs going this way, from top to bottom, left to right, and then diagonally coming from the left, and then diagonally coming from the right, and so forth, okay? And that's how your matrix is composed. Does that make sense?
Yeah.
You sure? Because like I know with what's the other one with the gamma camera, it was like quadrant 1, 2, 3, 4, and then you have to do all this subtracting, and then it goes into the X position, and then 1, 2, 3 subtract, and then it's the Y position. This is totally different. Basically, A and G go together, and then J and D go together, and then these go together, and those are what make up the little matrix. Okay? All right, so now we have, here we go. We have normalization scan, and that's done quarterly. Most important QC test. It evaluates the correction factor that are applied to every study. High quality image are acquired with very long acquisition time, which would be 12 hours. Scan a uniform source that's placed in the field of view, and it measures the response of each detector pair and it measures the response of each detector pair and used to obtain a correction factor that is applied to normalize the line of response that's passing through the source. So basically what it's telling you is that, is it reading whatever activity is hitting the detector within the reasonable time, okay? And also aiding with the correction factor. So it's performed quarterly. Images are acquired with a very long acquisition time, which is 12 hours, okay? So now you have uniformity, which is done daily, It's similar to a spec uniformity. The uniformity of reconstructed 3D images are measured and evaluated. You use cylinder solid phantoms with germanium-68 or liquid phantom that's filled with FDG solution. Okay? And then you have your window, your energy window calibration, and that's performed after repair or prior to a new normalization scan. Even though PET primarily uses 511 kV, it is important to evaluate the energy in order to separate scatter and evaluate the pulse analyzer. Do you guys have any questions so far?
No.
Okay. Jeremy, are you there? Are you okay? Jeremy, you're quiet.
I'm here. I'm listening. I got it so far.
All right, just making sure you're alive. All right, so then you have your PM tube gain test, and that's performed daily or weekly. The positron source of the known amount is centered within the gantry opening. The light output from each crystal is then predicted since the source is known. And then you have your PM can drift due to temperature and humidity changes, which makes sense. It's the same thing as the gamma camera. We want to make sure that the temperature and humidity stays the same at all time. Okay? Check to verify the response across the PM tube is uniform. Okay? So we want to, this you want to make sure that what you're putting in is what you're going to get out, because remember the PM tube, the purpose of the PM tube is to amplify the light that came in through the crystals. Okay? And remember, once it goes from light and once it gets into the PM tube, what does it convert into?
Electrons.
Correct. So you have to amplify those electrons. Okay? All right, now you have your coincidence time calibration, and that's performed weekly or quarterly, verifying that the detector block recognizes the line of response in the same timing window. And the system generates a histogram showing the time distribution of accepted coincidences, and it checks the system for changes in the histogram, and this is done automatically. All right, now this is your artifacts that you'll get in PET. The artifacts, the ray artifact is the same as the spec, and you use your, what's FBP? Come on, you guys. What's FBP? Filtered back projection?
Back projection, yeah. It took me a minute.
Oh, Lord. All right, so remember, it's the ray artifact is going to be the same as the spec, and then uses your filtered back projection. Now you have for motion artifact. Reconstructed image is viewed for motion, not the CNAs or cinograms as with the standard nuclear medicine or spec. Okay, it's going to be different. Then you have your misregistration artifact. If the patient moves during or between what and what scans that are acquired sequentially?
Transmission and emission.
Hallelujah. Exactly. This results in, believe me, I've heard between the PET and the CT. So that's why, exactly, okay? Between the transmission and emission scans that are acquired sequentially. This results in an invalid attenuation correction to the emission data. This would show on images as hot or cold abnormalities, specifically on the reconstructed emission images. Okay? So,
Put that.
I'm not telling you, and I can't tell you what class, but they did it. Between the PET and the CT scan. What?
Who's writing?
I am.
Who's?
Oh,
Perfect.
No.
On my paper.
No. All right. So this is what your ray artifact would look like. Okay. This is a coronal size, and then it's reconstructed with filtered back projection. Okay. I'm going back and forth like this because I'm trying to see what you guys have to fill in and what you guys are missing at the same time with the other with another slide.
Going back and forth.
You can't see me do this?
Oh, it was very subtle then.
See, that's how you do it. Exactly. Now this is motion artifact. See, your picture that you guys have is horrible.
Yeah.
And I'm looking at it now, that's why. I have a second screen. So that's how you know. You see the base of the skull is looking, oh, there we go. The base of the skull is looking a little special.
Mm-hmm.
That's no bueno. All right, then we have here misregistration artifact due to the respiratory motion. Okay. Lungs, or I should say, what happened here? Inhalation or exhalation? What is these? No. When you breathe in, what happens? Your lungs expand.
Right.
And your diaphragms are pushed down, and everything's pushed down, right? Is that correct?
Yes.
That looks
All right,
higher.
so that looks like what?
It looks like it's higher than it was. Or maybe I'm just tripping.
This is the compressed image.
Oh.
So this is your what? If you're breathing in, your diaphragm is pushed down. Is that correct?
Yes. Yeah.
So which one's the one that is inhalation? This one or this one?
The first one. Left side.
No, because this one.
Yeah, that's what I said.
Oh,
But I was pointing at this one.
Yeah.
This should be, did you say exhalation or inhalation?
Okay, so
This is exhalation. This is inhalation.
Okay, when you were pointing to the picture on the left,
Yes.
that's what I said, exhalation, because it's higher.
Sorry, I didn't hear exhalation.
Oh, okay, that's okay.
My bad. All right. Breathing out, breathing in. Okay?
Mm-hmm.
All right, so now we have artifacts in PET. So we have bed overlap, and it's caused by the overlapping from incorrect bed position during the whole body scan or the whole body study. And you need to acquire a new normalization study. Photopenic strips would appear on the coronal image. And then your other one would be hotspot artifact. And this occurs when a PET radiopharmaceutical is used as the transmission source. Any annihilation photons detected during the transmission scan will be assigned to the attenuation map. So what would happen is that you'll have lack of counts adjacent to the hotspot. How do you think you could fix this?
More scanning time? No.
More scan time. Interesting.
Lack of time to the spot.
More scanning time, she said.
Bend over. Hot spot.
If you have lack of counts, more scanning time will fix it. What could be another option? If there is another option.
filters.
Mm-hmm. Can you manipulate those filters on a pet?
I don't know, we haven't gotten there yet.
Well, you've never done pet, Robert?
I don't recall doing the filters, anything with filters.
Already done?
So who's worked with pet so
Yeah,
far?
I didn't realize it.
You did. You're right. I mean, I'm not saying you're wrong. You are right. You can manipulate your filters. You just have to know what filters they are that you're manipulating. Okay. All right. So this is your overbed. Oh, let me get back. Oh, your pictures are bad.
So
This is your.
Sorry. So the answer was filters, correct?
The answer is change. Increase your time and your filters.
Okay.
All right, so this one is your bed overlap artifact, where it's going to look photopenic. Okay. Wait, let me see. There we go. Okay. This looks like a really husky individual. And then here, hotspot artifact. Okay. And this is with no attenuation correction. And this is with attenuation correction.
Well,
So
it didn't work very well.
should that answer have been attenuation correction would have fixed this?
Where it says lack of counts, hold on, let me go into the lack of counts. Oh, I see what I did. Okay, so lack of counts. This is adjacent to the hotspot. Would be, that's your fill in the blank, right?
Mm-hmm.
And then you have that may fix this for your hotspot. It's not, what did I say? I said increase the time?
Increase time and change your filter.
Don't, okay, no. Okay, so scratch that. You even have this thing in here. And put your attenuation correction / filter. Okay? You guys want to take a break before we do CT, or you want to just dive right on into it?
It's gone. I do want to know how I can get a recording of